Hi, my name is Stephanie Lauber, and I'm here today to talk about my research benchmarking projected Hartree-Fock as an approximation. All of this work was done under the advisement of Dr. Calvin Johnson in CSRC in the Department of Physics here at San Diego State University. Before I get into the research, I want to talk a little bit about the big picture in nuclear physics. On the left-hand side, we can see the canonical nuclear landscape. This is color-coded by half-life in seconds. This was taken from NNDC in February 2021, so it was relatively up to date. Here we can see the most stable nuclei running up roughly the center of this currently known landscape with their half-lives color-coded in black. And as we add more protons and neutrons to those isotopes, we can see that the half-life decreases, which means they become more difficult to study experimentally. And we must turn to computational methods to continue to gather important information about these nuclei. One of the most successful of these computational methods has been full configuration interaction, but unfortunately, as you increase the number of particles or the size of the model space, we often run into a memory-bound problem with these computations. Instead, in this study, we turn to approximation methods that still allow us to gather important information on nuclei that are currently outside the computational limitations of FCI. Specifically, the approximation I'm looking at is projected Hartree-Fock. So this is convenient because we can use the same model space and the same interactions for a direct comparison between our PHF results and our FCI results. And we perform basic benchmarking in the SD and PF shells, which are small to moderately sized model spaces respectively. With that benchmarking in place, we turn to two areas of interest, that being germanium isotopes. These are known for having complicated spectra and shape coexistence that's evident by second and third low-lying 0+ states in the even-even isotopes. And then we turn to magnesium-40, which is currently untenable even using FCI, but it is interesting because it's the most neutron-rich magnesium isotope that has experimentally been created as of 2019. So the primary goal of this benchmarking study and application to larger nuclei is to investigate the computationally inexpensive alternatives and see whether or not they provide accurate results. One of our codes is just a Hartree-Fock code, and we have two methods to find the Hartree-Fock minima, one being diagonalization, which is more traditionally used, and the other being gradient descent. We first wanted to determine which method was better at reproducing a lower Hartree-Fock state and stable states. So here on the left-hand side, I have plotted a difference between the diagonalization and gradient descent. The important takeaway from this slide is gradient descent does better. It finds lower Hartree-Fock energies, and it finds fewer unstable Hartree-Fock minima. The nuclei with multiple stable minima were investigated using projected Hartree-Fock. And basically the benchmarking in our smaller SD and PF shells shows that projected Hartree-Fock is a valid approximation to the full configuration interaction. Our first difficult case is going to be the even A germaniums, or even. These have even number of protons and even number of neutrons. We can see in the blue is just using the first Hartree-Fock minima. In the black is our full configuration interaction results. And in the red is the addition of a second stable minima. In all four cases, we were able to produce a second 0+ state, which again is indicative of shape coexistence and a very good result for a very fast and simple approximation. We were also able to reproduce spectra that was more complicated, something more along the lines of what we would see in full configuration interaction or even experimentally. Specifically in germanium 66 and 70, we can see that the original excitation spectra was heavily rotational, but with the addition of that second Hartree-Fock minima, we can get something that better replicates our full configuration interaction. Finally, magnesium-40. So approximation methods are vital for calculations when the model spaces become untenable. Again, on the left-hand side is the first Hartree-Fock minima. In the center is comparison to experimental results because we cannot do this with full configuration interaction. And in red is the addition of a second minima. We are able to reproduce a state that is at least close in excitation energy to the second excitation state in the experimental value that is currently unknown. And going forward, we're looking to add additional Hartree-Fock minima, which we hope will improve the spectra even further. And we also want to apply this to other nuclei that are currently untenable in FCI, but do have experimental results that are available through sites such as the NNDC. Thank you for your time, and I hope this was interesting.